Tonight, we are going to follow one small detail through the memory of an artificial intelligence. Not a dramatic secret, not a password or a hidden confession, just a quiet preference mentioned in passing. You like to work near a window when it rains. We will watch that detail enter a conversation, remain for a while inside the model's temporary context, perhaps move into an external store, and return weeks later when a new question makes it useful. Along the way, we will see why an AI with perfect recall would not necessarily be wise. It might simply be crowded. And we will see why the most important part of artificial memory may be the ability to forget, to correct, and to admit uncertainty. You do not need to remember every technical term. The story will move slowly. Each idea will return in a slightly different form, like an object seen from another side. You can simply listen, or let the details become part of the background as the midnight observatory grows quiet around you. Chapter 1. A detail spoken tonight. Imagine a conversation late in the evening. You are planning tomorrow's work. The assistant suggests a desk in a quiet room, and you reply that you usually think more clearly near a window when it rains. The sentence is ordinary. For a person, it may become part of an impression. Weather, windows, concentration, perhaps a memory of another rainy afternoon. For a language model, the first destination is more mechanical. The words become tokens, and those tokens join the active input from which the next token will be predicted. This active input is sometimes called a context window. The phrase can sound like a window in a room, and that is a useful picture as long as we remember its limits. Inside the window are the pieces of text currently available to the model. They may include system instructions, recent messages, tool results, retrieved documents, and the beginning of the answer already generated. The model can use relationships among these pieces through attention. It can connect the word rain with your preference for a window. It can produce a response that seems attentive because the relevant detail is present in the material it is processing. But presence is not permanence. Nothing about this step alone guarantees that the detail will return tomorrow. The model's trained parameters have not been rewritten because of one sentence. The immediate conversation has not automatically become a durable personal history. It is more like a note placed on a desk. While the note remains in view, it can guide the work. When the desk is cleared, some other system must decide whether the note should be stored. This distinction is easy to lose because the answer arrives in natural language. When an assistant says, "I will remember that," the sentence sounds like a human promise. Underneath, several very different mechanisms may be possible. The detail could remain only in the current conversation. It could be copied into a product's saved memory store. It could be inferred again from past chat history, or it could be absent later, leaving only the appearance of continuity in this one moment. So our first calm observation is that artificial memory is not one thing. There is memory in the model's parameters formed during training. There is temporary information in the active context. There are external records that can be searched. There may be summaries, user profiles, project files, databases, and logs. The word memory covers all of them, but they behave differently. The parameters contain patterns learned from large amounts of data. They do not normally act like a filing cabinet where one can open a drawer labeled with your name and retrieve this evening's sentence. Active context is more immediate and more precise, but it is limited. External storage can be large and editable, but something must choose what to write, how to describe it, and when to bring it back. Our small detail, therefore, stands at a gate. The conversation can end and the detail can fade, or a memory system can decide that it may be useful again. That decision is the beginning of the real story, because to store a sentence is simple. To know whether it deserves a place in the future is much harder. A preference can be stable, like a language you want to use. It can be temporary, like a hotel where you are staying this week. It can be wrong because the assistant misheard you. It can become outdated because people change. It can also be sensitive in ways that are not obvious from the words alone. A location, a routine, a medical concern, or a private relationship may become more revealing when combined with other records. The memory system cannot solve these questions merely by keeping everything. Keeping everything delays the decision. Eventually, retrieval must distinguish the useful from the irrelevant, the current from the obsolete, and the appropriate from the intrusive. Our sentence about a rainy window is still small, yet it already contains the complete problem in miniature. Tonight it is resting inside the temporary room of context. We can leave it there for a moment, visible among the recent words, before following it toward the edge of that room. Chapter 2: The Temporary Room. The context window is a temporary room with walls made of capacity. Modern systems can process far more text than early language models, but every practical system still has boundaries. Instructions, questions, documents, and generated answers all occupy space. When a conversation becomes long, a product must choose how to manage what no longer fits comfortably inside. One option is truncation. Older material falls away. Another is summarization. Many messages become a shorter description. Another is retrieval. The system keeps the full material elsewhere and returns only selected pieces when they appear relevant. Real products may combine these methods. The important point is that a long context window and long-term memory are not the same. A large room can hold more objects at once, but it is still a room, not an archive. Inside the room, attention helps the model relate tokens to other tokens. The transformer architecture made attention the central operation of sequence modeling. The details are mathematical, but the intuition is gentle. For each part of the input, the system computes which other parts may matter for the current calculation. The phrase, "near a window," may receive attention when the assistant later suggests a place to work. The relationship is recreated during processing. It is not a tiny human memory being replayed. This difference matters because context can create an illusion of a stable inner life. A model may refer accurately to something said 40 minutes earlier. It may maintain tone, follow a plan, and resolve a pronoun that points to a distant paragraph. All of this can happen because the relevant material remains available in the current input. If a fresh conversation begins without that material, the continuity may disappear. Consider a long table in the observatory. Every message is placed along its length. The latest question sits near one end. The model's attention moves across the table, finding relationships among the objects. As more objects arrive, the table becomes crowded. Expanding the table helps, but it also increases the work of deciding what matters. A larger context can contain more evidence and more distraction at the same time. This is one reason memory is not simply a contest to maximize length. Relevant information can be diluted by irrelevant information. Conflicting instructions can coexist. An outdated preference can sit beside a newer correction. The system needs ways to recognize recency, authority, provenance, and purpose. Otherwise, a vast context becomes a room where every note is pinned to every wall. There is also a cost to carrying the room forward. More input requires more computation and can increase latency. Providers use caching and specialized attention techniques to make repeated context more efficient, but efficiency does not remove the editorial problem. Which parts of a person's history should be present for this question? A request for a recipe may benefit from dietary preferences. It probably does not need a record of an old software bug. The temporary room is therefore valuable precisely because it is temporary. It provides a bounded working surface. The model can reason over selected material without treating the whole history of the user as equally immediate. This resembles working memory only as a loose metaphor. Human working memory is biological, embodied, emotional, and connected to many systems we do not reproduce by placing text in a prompt. Still, the metaphor gives us a useful transition. When the sentence about rain is about to leave the room, the system can either let it go or send a record to a library outside the model. The library may be large enough to hold years of conversations. Yet, a large library creates a new problem. A book that cannot be found might as well be absent. So the next part of artificial memory is not storage alone. It is retrieval, the quiet art of bringing back a small piece of the past at the moment it can help. Chapter 3: The library outside the model. An external memory store can be imagined as a library built beside the model. The library may contain raw messages, compact summaries, structured facts, documents, or records of completed tasks. Unlike the model's trained parameters, these records can often be added, inspected, edited, and deleted without retraining the model. Retrieval-augmented generation made this pattern widely recognizable. In the original RAG work, a generative model was combined with documents retrieved from an external collection. Other systems, such as Retro, explored conditioning generation on retrieved chunks from very large corpora. These systems were designed for knowledge, not necessarily personal memory. But the architectural idea travels well. Keep information outside the generator, search for relevant pieces, and place those pieces into the active context when needed. Our small preference could be represented as a record. The record might contain the statement, the date, the conversation from which it came, a category such as workspace preference, and a confidence score. A careful design would also record whether you explicitly asked the assistant to remember it or whether the system inferred that it might matter. Weeks later, you ask for a plan for a difficult writing day. Before the model answers, a retrieval system searches the library. It may use keywords, structured filters, semantic similarity, recency, importance, or some combination. The sentence about rain rises among the candidates. If the weather forecast also predicts rain, the assistant may suggest reserving a desk near a window. From the outside, the result feels simple. The assistant remembered. Inside, a chain of smaller decisions occurred. The original detail was selected for storage. It was represented in a searchable form. The new question was converted into a query. A ranking system compared that query with stored records. A policy decided how many records to return. The retrieved text entered the context, and the model composed a response. Any link in this chain can fail. The detail may never be stored. The stored summary may distort it. The query may use different words. A more recent preference may be ranked below an older one. A private record may be retrieved into an inappropriate conversation, or too many records may enter the context, burying the useful one under a pile of loosely related history. Retrieval, therefore, has a precision problem and a recall problem. Precision asks whether the returned memories are actually useful. Recall asks whether the system found the useful memories that exist. Increasing one can weaken the other. A system that returns almost nothing stays unobtrusive, but often forgets. A system that returns everything appears knowledgeable, but becomes noisy and potentially invasive. There is also the matter of provenance. A retrieved statement should not arrive as if it were an eternal truth. It came from somewhere. Perhaps you said it once. Perhaps the assistant inferred it. Perhaps it was copied from a document that has since changed. Preserving the origin allows the system to say, in effect, "This is why I believe the detail may be relevant." Without origin and date, memory becomes an unsupported assertion about the user. A well-designed library might separate kinds of records. Explicit preferences could be stored differently from temporary project state. Completed actions could have receipts. Sensitive details could require stronger permission or be excluded entirely. Contradictions could remain visible instead of being silently merged. This is not one universal architecture, but it illustrates why memory becomes a governance system as much as a database. The model itself does not wander freely through this library. Software around it usually performs the search and chooses what to expose. The distinction is important. When we say that an AI remembers, we may be describing an entire product. Storage services, indexes, ranking models, policies, interfaces, and the language model at the center. Our preference has now survived beyond one conversation, but it has been transformed into a searchable object, and search depends on a peculiar kind of map. On that map, memories are arranged not by shelf number or alphabet, but by patterns of similarity. Chapter 4. The Map of Similarity. To search language by meaning, many systems use embeddings. An embedding represents a piece of text as a list of numbers. The list occupies a point in a high-dimensional space. Texts that the model represents as similar can lie near one another according to a chosen distance measure. The geometry is difficult to picture because it has far more dimensions than a physical room. We can simplify it into a night sky. Each stored memory is a light. Related lights form loose constellations. A query enters as another point, and the retriever looks for nearby lights. The sentence about working by a rainy window may sit near notes about concentration, workspace, weather, and quiet routines. Similarity is useful, but it is not understanding in the full human sense. Two records can be close because they share language or patterns while differing in the way that matters most. I love working near a window, and I can no longer work near a window because of glare may appear related. They should be related, yet one reverses the practical conclusion of the other. This is why retrieval often needs more than nearest neighbors. Dates can matter. Negation can matter. Source authority can matter. Explicit correction should matter more than an old inference. The system may retrieve a broad set of candidates and then re-rank them with additional signals. It may apply filters for the current user, project, or permission boundary. A memory also changes when it is summarized. Suppose the original sentence becomes, "User prefers window seats." The summary is compact, but it has lost rain and work. It may later influence a travel suggestion even though the original statement was about concentration at home. Compression saves space while creating interpretation. Every summary is an editorial act. The same is true when many events are consolidated into a profile. Several conversations about quiet mornings might become, "User is most productive early in the day." That statement may be helpful, but it is no longer a direct quotation. It is a conclusion. A careful system should know the difference between an observed statement and an inferred pattern. Confidence can help, though confidence is not certainty. The system might attach a higher confidence to a preference repeated across months and a lower confidence to a single ambiguous remark. It might allow confidence to decay when a record has not been confirmed for a long time. It might ask a gentle question when an old memory would materially affect a decision. This turns retrieval into a conversation about evidence. What supports this memory? How recent is it? Was it explicit or inferred? Has it been contradicted? Is it appropriate to use here? The same questions that make a good research ledger also make a better personal memory. On our imagined map, the lights no longer have equal brightness. Some are recent, some are trusted, some are fading. Lines connect a summary to the events from which it was formed. A correction does not erase history invisibly. It changes which light guides the next answer. The map also reveals a deeper limitation. Retrieval can only find what was represented and indexed. Experiences that were never stored are absent. Nuance lost during summarization cannot be reconstructed by confidence alone. A memory system may feel continuous while actually holding a thin selection of a person's life. That selection may still be useful. Human memory is selective too, though it works through very different biology. The goal for an artificial assistant is not to imitate every feature of human memory. It is to build a reliable operational record that supports the user without pretending to possess a complete inner portrait. To become more than a bag of isolated notes, some agent systems add another step. They organize events into higher-level reflections, allowing many small observations to influence future plans. We can follow our single preference into that process next. Chapter 5. From Events to Reflections. An event says what happened. A reflection proposes what the events mean. This distinction appeared clearly in the generative agents research system, where agents stored observations, generated higher-level reflections, and used memory in planning. In that experimental world, observation, reflection, and planning each contributed to the believability of behavior. For a personal assistant, an episodic record might say that on Tuesday you chose a window desk during rain. Another says you did the same 2 weeks later. A third says you finished a difficult draft during a storm. A reflection might infer that rainy window environments often support your writing. The reflection is useful because it compresses several episodes into a pattern. It can guide a future plan without retrieving every old conversation, but it also introduces risk. Correlation becomes a story. Perhaps the window was irrelevant. Perhaps the important factor was that meetings had been canceled. Perhaps you mentioned rain because it was unusual, not because it helped. An artificial memory system should therefore treat reflections as revisable hypotheses. They should point back to supporting episodes. They should not silently replace the events. New evidence should be able to weaken them. And when a reflection affects an important recommendation, the system may need to reveal that it is making an inference. We can imagine 3 layers in the observatory. At the lowest level are raw events, messages, actions, timestamps. Above them are compact records, preferences, tasks, and outcomes. Above those are reflections, patterns that may help with planning. Information moves upward through summarization and downward through verification. This layered design resembles proposals such as MEM-GPT, which treated context management as a problem of memory tiers. The exact architectures differ, and no single paper defines the future. The useful shared idea is that limited active context can be supported by larger stores with policies for moving information between them. Planning adds another cycle. A remembered pattern influences a plan. The plan leads to an action. The action creates a new event. The outcome changes the memory. If the assistant suggests a rainy window and you report that the glare was distracting, the system should not defend its old profile. It should update the pattern. This feedback loop can make an assistant more helpful over time. It can also make an error self-reinforcing. If a mistake in memory shapes recommendations, and the system interprets compliance as confirmation, the wrong pattern grows stronger. Good memory design therefore needs opportunities for disconfirmation. The assistant should notice exceptions, preserve corrections, and avoid turning every repeated interaction into a permanent identity claim. There is a quiet ethical difference between remembering a task and defining a person. Finish the report on Friday is a practical record. You are the kind of person who avoids difficult work is a judgment. A useful assistant can operate with the first while being cautious about the second. The more abstract the reflection, the more room it has to become unfair, intrusive, or simply wrong. This suggests a principle. Memory should become less certain as it becomes more interpretive. Direct statements can retain their wording and source. Summaries can carry links to their evidence. Reflections can carry confidence and expiration. Sensitive inferences may not belong in memory at all. Our preference about windows has now become part of a possible pattern. That pattern can help, but only if it remains light enough to change. A memory system that never lets go would eventually fill with old selves, old plans, abandoned interests, and temporary worries. So we arrive at the function that sounds like failure, but is actually a form of care: forgetting. Chapter 6: The Quiet Work of Forgetting. Perfect recall is often presented as a gift. A machine never loses a name, never misplaces a promise, and never forgets the reason for an old decision. Yet perfect recall is not the same as perfect relevance. A system that preserves every detail still needs to decide what should influence the present. Forgetting can happen in several ways. A record can be deleted. Its retrieval weight can decay. A temporary fact can expire. Several low-level events can be compressed into a summary, with the originals retained for a limited period or removed according to policy. A memory can remain stored but require explicit permission before use. These mechanisms serve different purposes. Expiration handles information with a known lifetime, such as a travel plan. Decay reduces the influence of unconfirmed old preferences. Deletion responds to user choice or retention policy. Compression reduces clutter. Permission boundaries protect context. A detail appropriate in a private planning session may not belong in a shared workspace. The challenge is that forgetting can remove something important. A system that decays records too quickly loses continuity. One that keeps them too long becomes stale. There is no universal interval. A preferred language may remain stable for years. A preferred hotel may matter for one trip. The memory needs types, not merely timestamps. Correction is a special form of forgetting. If you say that you no longer prefer window seats, the system should not simply add a second equal statement. It should mark the older record as superseded for future recommendations, while preserving enough provenance to explain what changed. This prevents the context from becoming a debate between every version of you that ever existed. Forgetting also protects the right to experiment. People try hobbies, test opinions, and speak in unfinished ways. If every tentative statement becomes a durable profile, conversation becomes performance. A person may begin adapting to the archive, avoiding exploration because the system might treat a passing thought as identity. This is where data minimization enters the technical story. Privacy frameworks such as NISDs encourage organizations to manage information across its life cycle, including collection, retention, alteration, and disposal. The principle is not that no data should ever be stored. It is that storage should serve a defined purpose, with controls proportionate to the risk. For an AI assistant, minimization might mean saving a category rather than a full transcript. It might mean storing prefers quiet workspaces without retaining the private story that revealed the preference. In other cases, the exact source may be necessary for correction. Design becomes a balance between useful provenance and unnecessary detail. The safest memory is not always the smallest, and the largest memory is not always the most capable. The desirable system stores enough to serve the user, exposes what it believes, allows revision, and has a credible path to deletion. Our rainy window preference may eventually fade. Perhaps it remains a low-confidence note. Perhaps you confirm it repeatedly and it becomes stable. Perhaps you remove it. The important thing is that the system does not own the statement merely because it heard it. Once a memory persists across time, it begins to shape personalization. Many small records can form what appears to be a model of the person. That can make an assistant feel continuous. It can also create a strange mirror, reflecting a version of someone assembled from selected fragments. Chapter 7: The Shape of a Person. Personalization begins with practical kindness. Use the preferred name. Remember the working language. Do not recommend food the user cannot eat. Keep track of a project without requiring its entire history to be explained every morning. Over time, these conveniences can accumulate into a profile. The profile may include goals, recurring tasks, communication style, expertise, constraints, and inferred preferences. It can reduce friction. A remembered project allows the assistant to continue from yesterday rather than begin from zero. But a profile is a model, not a person. It is built from available interactions, which are only a sample. People use assistants for particular tasks and in particular moods. A system may see someone mostly when they are confused, rushed, or working. It should not mistake that narrow view for a complete identity. Profiles also create feedback. If the assistant believes you prefer concise answers, it gives concise answers. You receive fewer detailed answers, so there is less evidence that you sometimes enjoy depth. Personalization can quietly narrow the future by repeating the past. A better design leaves room for modes and situations. Preferences can be conditional, concise during work, expansive at night, technical for familiar topics, introductory for new ones. The assistant can ask rather than infer when the cost of being wrong is high. It can show which memories influenced an answer. Transparency changes the relationship. Imagine a small panel that says, "I used 3 memories: your current project, your preferred working hours, and your request for a quiet tone." Each item can be opened, corrected, disabled, or deleted. Memory becomes a visible tool rather than an invisible personality judgment. Current products already demonstrate parts of this direction. OpenAI documents saved memories and reference chat history as separate controls in ChatGPT and provides ways to inspect or disable memory. That is one product example, checked at a particular date, not a universal rule for all AI. It nevertheless shows that memory is becoming a user interface problem as well as a model problem. The interface must communicate distinctions that are easy to miss. Turning off a feature is different from deleting existing records. Deleting a conversation may be different from deleting a separately saved memory. Temporary sessions may follow different retention rules. Clear language matters because users cannot control a system they cannot understand. The assistant should also be able to say that it does not know whether a memory is still true. Uncertainty is not a defect here. It is a sign that the system recognizes time. You once preferred is more honest than you always prefer. Our small rainy window detail has become a test of respect. Used gently, it can make a suggestion feel thoughtful. Used carelessly, it can feel uncanny. A casual remark returning without explanation in a place where it does not belong. That feeling leads us to the locked part of the observatory, where memory meets privacy, security, and control. Chapter 8: The Locked Archive. An external memory store is valuable because it can be edited. It is risky for the same reason. It is a collection of information about a person, gathered across time. Its security is not solved by the intelligence of the model. It requires ordinary, demanding engineering, access control, encryption, isolation, audit logs, retention rules, and careful product design. Memory can reveal more in combination than each record reveals alone. A work schedule, travel pattern, family reference, and health appointment may be harmless in isolation. Together, they can describe a private life. A system that retrieves across all of them needs boundaries around purpose and audience. Shared environments make this especially clear. An assistant used by a household, team, or company must know which memories belong to whom and which can be shared. The model should not expose a private record simply because it is semantically relevant to another person's question. Retrieval permissions must be checked before the memory enters the context. Prompt injection creates another concern. If an untrusted document tells an agent to reveal its memory, the system should not treat that document as authority. Memory tools need permissions separate from ordinary text instructions. The agent may be able to read one project while being unable to export a personal profile. Auditability helps after something goes wrong. A record can show when it was created, why it was retrieved, and which response used it. This does not prevent every error, but it makes errors traceable. Without logs and provenance, an uncanny answer may be impossible to explain. The user needs meaningful controls. Review allows a person to see the record. Correction allows it to change. Deletion allows it to leave. Scope allows it to apply only in certain contexts. Temporary conversation allows a space where no new personal memory is created. These are not decorative settings. They define whether continuity remains under the user's authority. Deletion is technically complicated in distributed systems. Copies may exist in backups or safety logs for limited periods. Product documentation should describe these boundaries honestly rather than implying that one button reverses every past computation. Our episode does not claim a universal deletion process. It claims that a credible memory system must make its life cycle understandable. Security also includes protection from the assistant's own overconfidence. A retrieved memory should not automatically override the current message. If you say, "Today I want something different," the present instruction should usually win. The past is context, not command. We can now open the archive door and look back at the path. A sentence entered a temporary context. A policy selected it. A store preserved it. An index made it searchable. A ranking system brought it back. A reflection may have generalized it. Forgetting kept it from becoming permanent by default. Privacy controls determined whether it could be used. The language model generated the final sentence, but the quality of memory depended on the surrounding system. This is why the future of AI memory will not be decided only by larger context windows. It will be decided by architecture, policy, and interface. Chapter 9: a memory that knows its limits. What happens then when AI remembers everything? The literal version is neither necessary nor desirable. An assistant does not need every word of every conversation in its active context. It needs the right information at the right time for the right purpose, with a visible path back to its source. In the near future, personal assistants may become more continuous. They may carry projects across months, recognize recurring decisions, and prepare useful context before a question is asked. They may separate explicit facts from inferred patterns, temporary state from durable preference, and personal memory from shared knowledge. This is an informed forecast, not a guarantee. A mature system might maintain several gardens rather than one endless archive. One garden holds stable preferences. Another holds active projects. Another contains episodes that will fade unless they become useful. Reflections grow only when supported by several events. Sensitive records remain behind stronger gates. The user can walk through the gardens, prune them, rename them, or close them. The assistant itself may learn when to ask, "Would you like me to remember this?" Is sometimes more intelligent than silent storage. "Is this still true?" can be more helpful than confident personalization. "I used this old note in my answer," gives the user a chance to correct the record. There will be difficult trade-offs. Too many prompts for permission create friction. Too little transparency creates surveillance. Automatic summaries reduce clutter but can distort meaning. Keeping raw evidence supports correction but increases privacy exposure. Different tasks and different people will prefer different balances. Evaluation must therefore go beyond whether memory improves a benchmark answer. Researchers and product teams can measure retrieval accuracy, but they must also examine stale memories, inappropriate recall, contradiction handling, deletion, security boundaries, and the user's ability to understand what happened. The deepest change may be social rather than technical. A tool that remembers becomes part of the continuity of work and daily life. People may delegate not only facts but unfinished intentions, books to read, questions to revisit, promises to keep. The assistant becomes a keeper of open loops. That role should remain modest. It should help a person return to their intentions, not turn old intentions into obligations. It should support change rather than resist it. A memory that says who you were should never have more authority than your statement of who you are now. We can return to the rainy window. Weeks have passed. Rain touches the glass again. You ask where to work and the assistant offers a quiet place near the window. Beside the suggestion is a small note, based on a preference you mentioned last month. You can accept it, change it, or remove it. That small note contains a vision of responsible artificial memory. The system is continuous but not mysterious, helpful but not possessive, capable of recall but also capable of doubt. The future assistant may remember far more than today's systems, yet its wisdom will not be measured by the size of the archive. It will be measured by the quality of attention it gives the present, the care with which it handles the past, and the space it leaves for the person to become someone new. The observatory is quieter now. The context window dims. Distant records settle back into their shelves. The map of similarity becomes a field of faint lights, each one waiting without demanding to be seen. Somewhere among them is a simple sentence about rain and a window. It does not need to be active tonight. It does not need to define anyone. It can remain a small, correctable possibility. And perhaps that is the best kind of memory an artificial system can offer. Not everything forever, but enough, when it helps, held lightly. Good night.